Hello and welcome back. Let's see if this works better. This is the part 2. I will wait a few seconds for you guys to get on, and then go from there. So I restarted and I think it's working. Should be working fine. Yeah, this looks like it's going to work nice. All right, so to recap, we have a 0.5 kilogram mass. The spring needs to stretch 2 meters with a force of 100 newtons. We have initial position and initial velocity. So let's see what we can get. So we first calculate with the information given. We first calculate the spring constant, which worked out to be 50. And then we go and write our equation using M and using K of 50. Once we have the equation, we solve the equation using our regular characteristic equation, and because the answers happen to be complex, we are writing the solution, and the solution is x of t, a cosine 10t plus b sine 10t. That's the standard solution that we have for wave, right, in 2D. Now we have to use initial conditions to calculate values for a and b. So let me actually do that. Need initial conditions to calculate A and B. So we have condition x0 equals 1. So that's something that is given to us. What this means is x of time 0 is 1 meter. So that means when t is 0, x is 1, which means that we can use, let's label this as equation 1 and equation 2. So we can use equation 1 to say 1 is equal to a cosine of 0, because 10 times 0, t is 0, right? 10 times 0 plus b sine of 0. And now we're going to say 1 is equal to cosine of 0 is 1 plus 0, so we got that a is 1. Shouldn't it be negative 50? Negative what 50? Oh, you mean negative 50 here on K. No, because in mathematics we don't really use negative sign. In physics, you use it for reference purpose to describe that the spring is always doing opposite of what you want. So if you stretch, the spring wants to compress, and if you compress it, the spring wants to stretch. So in physics, you would put a negative sign there. In mathematics, because we don't deal with that, we deal only with calculations, we do not put a negative sign on that value. Also, if you remember, eventually it gets squared anyway, so it loses, but minus, but whatever, right? So no, we're not going to use a negative 50. And from equation number 2, we have negative 5 meters per second. Now that sounds weird, right? But the object is moving to the left. That's what it means when it's a minus for velocity. So V0 equals negative 5 meters per second means time equals 0, velocity equals negative 5. So from the second equation, we have negative 5 equals negative 10. Now A was calculated to be 1, and we have sine of 0, plus 10, we don't have B, and we have cosine of 0. Cosine of 0 is 1, so this term dies completely. And we are calculating negative 5 is equal to 10B, cosine of 0 is 1, B equals to negative 1/2. So now we are going to put all of this into our equation of x in time, right, is equal to A, which is 1, cosine 10t minus 1/2 sine 10t. Now, we can do better. We can calculate literally everything else using this equation. Remember what the list is. We're going to compute the time lag, the frequency, the period, all of those goodies that we had from before, and we're going to put it in the formula which shows the phase shift and everything else. So let's go and calculate these things. We recall that x of t was c cosine of omega 0 t minus, they called it alpha, so I'll keep calling it alpha. C was calculated, right? C was calculated as the square root of a squared plus b squared. So we are going to compute C by simply writing 1 plus negative 1/2, well, both are squared. So C is going to be the square root of 5/4, which is root 5/2. Right? Negative 1 squared is 1/4, and then 4/4 plus 1/4 is 5/4, and then square root of 5 stays, and you have a half there. So C is equal to that. We know omega t, so let's write what we have so far. We have root 5/2 cosine 10t minus alpha, right? Now, the question is, what is alpha, right? Well, we don't have to break our heads there because we have a triangle. And we can use the tangent from the triangle to calculate alpha. If we have our triangle with A, B, C, and alpha, and we know that A is 1 and B is -1/2, we need to carefully figure out which quadrant is this in, so we can calculate a correct tangent, right? So I'm going to actually just cross this out and do this in the coordinate system, so it's better, it's clear this way. I have A as a +1. I'll use 4 squares as 1. And then I have B to be -1/2, which is here. So here's the triangle. That's the 4th quadrant. And that's the alpha. We know that the tangent is negative in the 4th quadrant. So we should be expecting a value, right, as a negative alpha. So what are we going to have here? Well, the reference angle alpha is going to be 1. So let me put 1, and this is 1/2, and this is 1, right? Okay. So it's opposite over adjacent. So tangent alpha is going to be 1/2 divided by 1, which is 1/2. So alpha is inverse tangent of 1/2. When you pick up your calculator, the first thing you must do is check mode and make sure you're in radians. Otherwise, the whole problem is going to go to hell. All right? Well, it's already there. The whole problem is going to be wrong. So make sure you're in radians, then go inverse tangent of 0.5, and that will give you 0.4636 in radians. And now you have to take that away from 2 pi, because you calculated the reference angle. You calculated this. But what you need is that. So we have to go 2 pi minus 0.4636 in your calculator. And that will give you 5.8196. when you subtract and round. And that's your alpha. So now what you have is the solution x of t is equal to square root of 5 over 2 cosine 10t minus 5.8196. Yes, you could use the exact values, but now that you have this as a decimal, you might as well convert this into the garbage as well, but whatever. Okay. So the question is, what is the frequency, what is the period, and all of that kind of stuff. So, period. There's so much lag. It's driving me crazy. Period. Okay, I did not use -1/2 because I decided to use reference angles. If you use -1/2, then you do not have to use reference angles. It's up to you. It's harder. In my opinion, reference angle is easier because you compute reference angle always towards the closest x-axis, and then you just add pi, subtract pi, or subtract from 2 pi, and that's it. Period t is going to be 2 pi over omega 0. In our case, 2 pi divided by 10. That's pi over 5. And if you want the value for that, so that's going to be pi divided by 5, about 0.6283 seconds. So what does this mean? This means that the motion repeats every 0.6 seconds. The same motion repeats in that time. Frequency is going to be 1 over t. Well, frequency is nu in this case. Frequency nu is 1 over t, which is 1 over 0.6283. So now when you take this answer and you invert it, you get 1.5915 1 over second, which is known as hertz. Hertz is the measurement for frequency. And finally, we can compute the time lag, which is known as delta, which was alpha over omega 0. Our alpha was 5.8196 divided by omega 0 was 10, 0.582, whatever. And that's it. We got it all. Why'd you use 5.8? If you are referring to the time lag, this is your alpha here for the problem. This is your alpha R, alpha reference alpha. So this is the reference alpha, and this is the real alpha. This is the alpha that we need once you use the reference angle to compute it. I think we beat this problem to death. There is nothing else. We can graph it, and that will be it. So this is what a simple harmonic motion problem looks like when you do not have C involved. Once you get the C involved in the problem, then the problem becomes harder, because clearly we have more calculations, more options, more outcomes, and but again, it actually models the reality. So that's what we have in terms of so next problem is the free damped motion, where we involve the C. What are the units of time lag? Oh, okay, that's a great question. Let's derive it. Sorry, I didn't mention that before. So I just need to go and find where I have the time lag. There it is, time lag. So your angle is in radians, right? So radians divided by angular velocity is radians per second. And when we work out the double fraction, seconds will go on top, and these guys will cancel, and you would have time given in seconds, right? Time lag. It's time, and the time lag is also time. So the units will be, in our problem, would be seconds. That's the time lag. I just hope nothing crashes over here. There it is. So, quick summary for the problem, or a quick summary for the whole thing? Because if you watch it again, I mean, you follow the whole problem. I'm really running on fumes here in terms of the bandwidth. I would rather go on to present the second part of the lesson. I have another lecture scheduled, another class in 30 minutes, so I'm just going to continue. You can re-watch the video. That's the good thing about this, is it will stay on the channel. I am still detecting lag over here. The tablet starts lagging, is lagging again. I am not sure if it's overheating or something. No, I don't know, guys. It's just 11 o'clock is. So the second part of the lesson is the free damped motion, which is when you introduce constant C, and that's the one that the object will actually stop. So the object will be stopped in terms of the pendulum. It will be stopped by gravity. In terms of the spring, it will be the friction, and so on. So there are reasons why the object will stop. So now our main equation is mx double prime plus cx prime plus kx equals to 0. This is our equation. We are introducing the damping constant c. And now, again, we would like to have m gone from the first term. So we are dividing everywhere by m again. And the equation becomes x double prime plus 2px prime plus omega 0 squared x equal to 0, where omega 0, we already know, is the square root of k over m, and p is given as c over 2m, and it's always larger than 0. Remember, these problems do not work for c smaller than 0. We only have a situation when c is equal to 0. Again, we are modeling reality. Can you do it mathematically? Yeah, but if it's not significant, we're not going to worry about it, right? So, mathematically, you can do anything you want in life. So, we're going to do the, in this case, we are going to do, so this is for c larger than 0. And because c is larger than 0 and mass is always positive, right? Because mass is quantification of physical existence. It always has to be a positive number of some kind. So positive divided by positive is positive. So p is always positive value as well. All right, cool. So now we go and we do our characteristic equation to solve this. So r squared plus 2pr plus omega 0 squared is equal to 0. So this one now we can easily factor, right? And no, sorry, not factor. We use the quadratic formula. R12 is, so negative b plus minus square root of b squared minus 4ac divided by 2a. Perfect. So now we kick out 4. So we'll have 2 square root of p squared minus w squared divided by 2. The 2's will cancel for both parts of the fraction, and we get our R12 to be negative p plus minus square root of p squared minus omega 0 squared. I forgot omega 0. There we go. Omega 0 squared. And now, the solution clearly depends on the relationship of p and omega. If p is larger, then the value under the square root is going to be positive. And if omega is larger, then the value is negative. And those are the different cases that we see in the nature as you let something oscillate, right? So we have our values to plug in. So need to analyze p squared minus omega 0 squared. That's what we need to analyze. And once we understand that one, we will be able to set aside 3 cases, right? Because the value under the square root could be positive, negative, or it could be 0, right? So we will have 3 possible cases here. Well, remember that the p was c over 2m. So P would be replaced by C squared over 4m squared. And omega 0 was the square root of k over m. So when square will kill the root, so it's just k over m. So this is what we have. And we do the common denominator, which is times 4m on both of these. And we get c squared minus 4km divided by 4m squared. Now, 4m squared is always positive, so we don't have to worry about that one. So we only need to worry about c squared minus 4km. That's what we have to worry about. Because that is the value which determines whether the number in front under the square root is positive, negative, or 0. So this is where we find what we call critical dampening. Critical damping. Critical damping, and that's going to be C critical is square root of 4km. Which you can also say 2 square root of km, but whatever. And now we are able to define 3 cases, 3 different solutions. We have 3 possible solutions. Number 1, overdamped. Case, and that is where c squared is larger than 4km. This is where you get x of t equals c1e to the r1t plus c2e to the r2t. Oh, by the way, you know all 3 cases. We are now just putting them in a wrapper of physics. These 3 solutions you are going to get now are the 3 solutions that we had before in our cases 1, 2, and 3 in lectures 3.1 and 3.2 and 3, whatever we did. I know it was split in between different sections. The next one is critically damped case. Where c squared is equal to 4km. This is where you have repeated roots. So x of t is going to be e to the negative. Now we use pt because we are in our mode for physics. And the third case is underdamped case. Where c squared is less than 4km. And this is where you have your complex solutions. And this is the one that can also be represented with the phase shift, right? There we go. Same solutions as before. So we know how to solve every single one of these cases because we did a lot of these cases so far, right? The examples of this are given to us in previous lectures. Now we just, okay, let's do a word problem that, focuses on one of these. They all solve the same. You will write differential equation, you will do the characteristic equation, that will give you some values for R, and whichever case falls under, that's what you have. If it's going to have some kind of oscillation. It's worth mentioning here on a third one. This is a really cool thing to understand. Off of this solution, to draw the graph. Actually, no, off of the one solution on the bottom. Right? If I am to draw the graph for this, I will draw the cosine graph which decays in time. This is my time axis. This is my x-axis, right? So we go and we can put decay on the graph, and then fill in the cosine so that decays in time. Since x measures the distance from the equilibrium, we see that the distance from the, so this axis here, this is where equilibrium is. Distance equals 0 there. So when you put your spring and you have your object here M, you stretch it here, it will fly past to this point, it will fly past, but it will end up shorter, then will go back, will end up shorter, then goes back, ends up shorter, and it keeps going until it stops in the middle. You see that this distance d, is measured here in a vertical sense, and as the time progresses, the distance from the equilibrium is less and less and less until it stops. So this term is the one that it's introduced because we had dampening system now, right? In terms of, in this case, it's friction that stops because the object rubs against the floor. In terms of the pendulum that it's hanging, it's gravity and air resistance. So all of those factors put together make the object eventually stop. And that's what we are when we introduce dampening constant. Now, previous case, the part 1 of this lecture had the case when C was 0, which is no friction, or you are doing this experiment in in a space far away from all the galaxies. There is no gravitational pull on it, therefore pendulum would swing forever and would never stop. There's no air resistance because you're in a vacuum, no gravity because you're really far away from everything. So that's that. And now you can do the same problem we did earlier. Just introduce C, and that will slightly change your equation. You do characteristic equation, you do everything the same. So if your mass is 1/2 of a kilogram and your spring constant K is 50 newtons per meter, and you introduce dampening, where C is given to be 1, that's also given to you. Your equation becomes, remember that your equation is this. You plug in the values. You multiply the whole equation by 2 to get x double prime alone, meaning coefficient 1. Now use r squared, which is characteristic equation, to solve the problem. Use negative b plus minus square root of b squared minus 4a c, which is minus 400, divided by 2. It's negative 2 plus minus square root of negative 396, divided by 2. I can factor out 4, so I can cancel these 2's. I could have factored more. So r 1/2 is negative 2 plus minus 2 square root of negative 99 over 2, so I can cancel these 2's. That's going to be negative 1 plus minus I square root of 99. Now I can kick out a 9, which would make it 1 plus minus 3 root 11 I. I don't like it. I'm just going to keep it root 99. I root 99. It's nicer looking. Yes, you should be simplifying it, but just please don't put decimals. I mean, yes, in engineering you do the problem in physics and stuff, you put the decimals, but in math just leave it. Don't bother it. Don't make it ugly. And guys, we have the E part and we have the omega part, right? So we have the case where it's underdamped, right? So we're going to do x of t is e to the negative t, right? Because it's negative 1. And then we have a c1 cosine root 99 t plus c2 sine root 99 t. Then use initial conditions. To calculate C1, C2, and so on. Obviously, for C1 and C2, you will have to do product rule to differentiate this into velocity, then plug all of the values. So it's going to take some time. And then you can also calculate, if you want, your frequencies and everything else. You can also compress it into the phase form and so on. So there's a whole bunch of cool things you can do. And now you know why pendulum stops. You can do the calculation for pendulum. And one of the problems I am thinking on posting is for you to actually attach a pendulum of some kind. Take a piece of string, or rope, or a bendy wire, and suspend something off of the ceiling, or a shower curtain rod, or somewhere. Suspend some object, and then give it a whack, and see. You can measure. You can count the seconds. And then see how well your calculation matches the reality of the experiment. So that's it for now. I'm going to post the discussion in Canvas for exam. I have another class starting in 9 minutes, so technical difficulties and the length of this lecture prevented us from talking here in chat about the exam. My hope is that you will all log to Canvas and discuss the possibility of running the first exam next Wednesday. The exam was supposed to be today. The exam was supposed to be last week. Then, because this is the first week back, it was supposed to be today. But then I am going to open that discussion now, and I will leave that discussion by the end of the day, because if we are all agreeing that exam 1 because we still have exam 2, exam 3, and the final, and the class ends in a month and a half, so yoo-hoo, right? We have full April and half a May for the class. The March is already done. Today's 25th. So we'll have to deal with that. I'm going to open now in announcements, and I will allow posts in announcements. Go to announcements at some point today and voice your opinion, and then we'll make the executive decision whether the exam should be on Wednesday, and I will reopen the quizzes. I need this today because I need to open the quizzes online for you to practice and score points prior to exam. Exam will be on my MATLAB, and we already talked about the format and the time and all of that stuff, so you already know that. I am going to leave now, and I will see you all online on Canvas. Bye.